So now that we've defined our approximation space, we'd like to be able to define our weighting space as well. Specifically, we'd like to determine what the basis for our weighting space is so that we can determine the form of our basis functions for our weighting space. So we'll cover this in a little more detail in Module 3, but we'll take this, the DG approach will take the same approach that a finite element method would take, in that it chooses the space of the weighting functions to be the same as the space for our approximation bases. So in other words, this was our space that we used for our solution approximation, and our weighting functions live in that same space. So we'll choose our weighting functions to be the same as our weighting basis functions to be the same as our approximation basis functions. So the 0th term for the weighting function will be identically equal to the approximation bases, and same thing for our second term here. So in order to solve the approximation, we have to satisfy the weak form solution for each weighting function. So when we think about our weak form, we had the derivative of our conserved quantity with respect to time times some weighting function plus the integral of the derivative of the flux with respect to space times our weighting function. And we left these without any subscripts for our weighting functions, but really we need to satisfy these for each of our possibilities. So if we denote these as jth basis functions, we need to satisfy this for all j. So this means that we will have, in the case of our linear solver, we'll have two sets of equations then, one for the 0th order term and the other for the 1st order term.